So good evening, one and all. We welcome you all towards the end of our session on research methodology workshop. So today we have with us Dr. Chris Andrews with us to talk about the basics of statistics. So we have this class in two parts, one this Thursday and the next one on 24th. So Dr. Chris finished his BA and Masters in Mathematics from the University of California, Berkeley in 1992. And after that, he did his PhD in Statistics from 1993 to 97 from the Carnegie Mellon University. And after that, he joined as an assistant professor in various colleges. And in 2005, he shifted to the University of Buffalo, where he was a graduate and undergraduate director. And in 2012, he joined the University of Michigan, where he works till present. And he's the statistician expert there and in the Department of Ophthalmology and Visual Sciences. He also serves as a lead biostatistician for the Northeast Regional Center of the Women's Health Initiative. Over to you, sir, for your discussion on basic statistics.
Great, thank you very much for that introduction. I am honored to be able to present to you. This is the first time I've talked to the Airman group here in India, so I'm a novice in that way. I hope everything goes well. I'm going to have some slides up during the presentation here, and I hope that you will interact with me if necessary. So if you have questions, please help me out. I don't think I can get any chats during the Zoom session, so you may have to speak up to let me know. Let's see. Is my screen now showing my slides?
Yeah, we are seeing full screen, sir.
Okay, great. Thank you. Well, thank you for the introduction. I was going to say much of what you already said about me. I've been around to several different schools. I've been working as a professional statistician for about 25 years. And a lot of what I do has been the same over time. A lot of statistics is starting from the basics of describing your data and then tailoring your analysis to what the research aims are. And so we're going to talk today about what some of those basic methods are, and hopefully you'll take away some of the things you need to think about when you're doing your own research and when you're reading other people's research. I'll say it again here. I'm going to try to stop often for questions, but if I'm not stopping at an appropriate time and you have a question you want to ask, please try to interrupt me. Statistics comes in two varieties, mainly. Descriptive statistics, which is describing the data that you actually have. Data are very valuable, just about the people and the units that you're studying, and you want to know what you can about that specific group. You want to know what's special about them, what's not special about them. Are there trends? Are there unusual observations? So the first piece is always to understand the data that you actually have. Second part is trying to say more about the data you don't have. Often data are collected from a sample of a larger population, and you really want to say something about that larger group. And that's called inferential statistics. What can you infer about a larger group based on the little bit of data that you have? And it's not always appropriate to do inferential statistics. I know that if you read a medical journal, just about every statistic comes with a p-value or some type of confidence interval. But that sometimes is just force of habit and isn't always justified. And we're going to talk about inferential statistics next week for the most part. And I'll talk about some of the benefits and dangers of of p-values and statistical inference. So while you should always do one, descriptive statistics, to understand your available data, it's not always necessary or appropriate to move on to inferential statistics. This is a list of what I was asked to talk about, or a few ideas of things I could talk about this week and next week. And so I'm going to focus on these, not quite in this order, and not all today and not all next week. But how do we make tables from data? This is the heart of descriptive statistics. What are the various formula we use to apply during statistical analysis? So some of them, the ones today, are very simple and straightforward. The ones about inferential statistics get more complicated. But fortunately, computer software will do all of these if we learn how to do it. So although I'll present a few formula, I'm not going to spend too much time on that, because it's more important to learn how to do some of this on a computer. And that brings us to 3, what software is available for statistical analysis. Of course, there are many. What's available particularly to you will probably determine what you choose to use, and we'll talk about the benefits and drawbacks of each of several software packages. How do we interpret results is quite wide-ranging, and that's where it's more problem specific. There are certainly some general guidelines that we can try to apply, but this is where statistics kind of interacts with the field, whether it's medicine or sociology or economics or whatever. And the interpretation certainly is informed by the statistics, but much of the interpretation has to come from the prior knowledge of the specialist. And that's why I find being a statistician very rewarding, because although I spend almost all my time doing the statistical analysis, I get to discuss the implications of what I found and what the doctors are expecting, and how those things overlap or disagree. And so the interpretation is usually a collaborative effort and is problem specific. So we'll talk about some guidelines of what to look for, but a lot of that will just come from experience with your problem at hand. And finally, what do we need, and how do we do a sample size calculation? I'm going to rephrase that a little bit, in that sample size calculation is one piece of study design. And although I'm going to spend almost all of today talking about analyzing data that you already have, the number 5, the study design, is actually a very important part of the best statistical plans, best statistical analyses. If you can figure out what data you need and how to collect it reliably, then you can, there's a better chance that your results at the end will be informative to you and others. Part of planning a study, besides what data to collect, is how much to collect, and that's where the sample size or power calculation comes in. So it all starts with data. At least today, it's all going to start with data. We'll talk about planning next week. But you have to store your data somewhere, and this has changed over the history of statistics. It used to be, tally marks on a sheet and counting things up. Now data is almost always stored on a computer spreadsheet for basic analysis, for basic record keeping, I should say, just a simple spreadsheet does a lot. Often you have to extract data from, say, an electronic medical record and store it in a convenient format. And there are plenty of spreadsheet programs available to do that. When you're collecting data, one thing you don't want to be stuck with is difficulty recording things. So if it is easier to write things down on your own sheet of paper or type things into a document and then later pull out the exact data you need, that's okay. There's no one way to get data from one source into another. One thing you don't want to do is start collecting data, realize you've missed something, and go back and have to do it again, or throw out your early data because you didn't collect the right information. So there's some good planning there, and your data sheet can help you organize your thoughts there. This first data storage approach of just collecting the information you need is helpful to you. You can see what's going on in your data. Often it's easy to input, but eventually it needs to be an analysis file that a computer can read. So I've got a couple data sets here. Here's an example from a project I worked on in the last few years. And I want to point out some things that either are good for humans or good for computers. This is Microsoft Excel. It could be Google Sheets or any other number of programs. First of all, this data sheet, when it first arrived to me, had a medical record number in it. That's not something you want to just be passing around in data sheets to everybody else. I've deleted it, and not just for this presentation. I deleted it as soon as I got it. I knew I could go back to the physician who supplied it to me if we somehow needed to go back and get more information. It's much better to have a study ID or something else that is not immediately identifiable. You're not going to find any names in here or social security numbers or addresses. I only want that in here if it's really important to the analysis. But then here I want to point out that, what is this, duration of visual symptoms was missing for this one person. And I want to point out a couple things. First of all, this color is very useful for me as a person to be able to see that there's a missing value there. Similarly, these green ones. But the computer, when you read this into a stat package, can't tell green from yellow. So if there's a difference between these two NAs, not applicables or not availables, the statistics package isn't going to be able to tell. And so while these may be good reminders for the humans, colors are not good for computers. But this was kind of an initial file, and we cleaned it up for use in an analysis. Here's another example of a cell that is going to be difficult for a computer to use. This is not a number. It's a number followed by another number, and this will be read in as a string, and then all of a sudden this isn't any number at all. And you know, I know what these things mean, but the computer is going to have a hard time with something like this. So we're going to have to think about how to process something like that. Over here, there's kind of free text written in, and that's going to be difficult for a computer to summarize in any way. So if there's some kind of useful information in this operative note, the computer probably isn't going to be able to pick this out easily. We are going to have to do something about it. And actually, this variable was one attempt to do that. A resident went through the operative note and looked for certain features. And if they saw it, they recorded a 1. And if they didn't see it, they saw a 0. So this is something a computer can do something with. One last comment about this data set is there's a blank cell here. And this, when read in by a computer, will be treated as missing data, which it probably is. But notice how these were actually recorded as not available. Somebody went looking for this change in visual field, and it couldn't be calculated, or it couldn't be found. And so they made a mark of that. If you leave a cell blank, there's some ambiguity. Did you not get to this patient yet, and so you still need to look at it, or did you look for it and it's not there? So generally, when you have a completed data set, you don't really want empty cells, because there's uncertainty about whether you actually finished collecting the data or not. And it's an empty cell somehow different from an NA. So while collecting data, feel free to use colors and abbreviations and free text to record what you've observed, so that you don't have to go back to the person or the record again. But eventually you're going to have to process it into what I like to call an analysis file. And this is much more structured and easy to deal with for a computer. The basic structure, and not all data files are like this, but the vast majority of them are. Each row is an individual. And for an analysis file that you're going to read into a computer package, don't have a row at the bottom that computes, say, the average of every column, or the count of the number of observations or something. Try to have your data file be just your data. If you're going to do some analysis in your spreadsheet, make it a separate spreadsheet. Have your data file in one place. You can copy and paste it into another and do some analysis in Excel or whatever. I'm not promoting that. I don't want to put that out there. But I know plenty of people have access to that and want to do at least some initial calculations. So try not to put those in your original data set. So each row should be a person, not a summary of people. Each column is a separate variable. Don't put several variables in one column. One example I've seen of this is sometimes I'll get a systolic and diastolic blood pressure in a single column, separated by a slash or spaces or something. Just put each one in a separate column. We're going to deal with them as numbers. Let's keep them as numbers separated and don't put any extra text in. For vision, you saw a bunch of the columns that I had being reported was visual acuity, and it was 2200 or 20/40. Those can be recorded. If the numerator is always 20, all you need to do is record the denominator. You'll save yourself time typing, and you'll have easier time analyzing the data when it's over. I've already mentioned that statistical packages do not read color. So if the color is important to the computer and to the analysis, and not just to the human looking at the file, convert it to a categorical variable somehow. So maybe you'll have a column that just says, what color did I highlight something? And you'll type in red or green or yellow to indicate certain things. Or you might type in actually what that represents. These were collected by one investigator and these others were collected by another investigator. Maybe that's what the colors meant, and just need to put them into a variable. Don't leave a cell empty. Put either an NA or a dot or something to indicate that you did look for that data, it wasn't there, maybe even put a note about why it isn't there, although that would be best for a separate column, but just about notes about the data. And I made this point already, don't include unnecessary sensitive information in an analysis file. Later, you'll be sharing this analysis file with a colleague who wants to ask a slightly different question about the data or whatever. If there's no reason to have sensitive information in a file, don't put it there. You need to keep that information somewhere else in case you need to know exactly who this person is so that you can get more information or do follow-up care. But that should be in a separate informative information file. It's not in your analysis file for statistics. So I spend time on this because although I'm a statistician and occasionally get to do some very creative analyses, I spend a lot of time working with data, and getting a data into a usable format is time consuming, but valuable. So if you can get your data organized well, the analysis of it will be much more straightforward. Let me just pause and see if anyone has any questions or comments.
So regarding this missing value symbol, if we put a dot, would that be counted, or it wouldn't be counted for the analysis? Or do you say even if we leave it empty, it wouldn't be counted, right?
Yes. Okay. So there we get into what do you do when you load your package into a statistics spreadsheet. I use R and SAS most often, and when you read in data, you can say a missing value is indicated by a dot or an NA or something. And so when you read in the file, the statistics package will understand that there's missing values. And we'll treat it correctly. If on the other hand, you're using, say, Excel to analyze your data and you want to use a count, the equals count something or other, yes, it will count that as an observation. But when you do a summary of the data, if you ask it to compute a mean, it'll ignore the text there. It'll ignore the NA. And if you tabulate things, count up frequencies and percentages, it will treat that as a separate group. And so you'll know how many missing data you have and things like that. Good point.
Thank you.
Yes. So missing data is a difficulty we almost always have to deal with. Sometimes cases or observations, individuals who have missing data are removed entirely from an analysis. Other times, more advanced techniques are used to deal with the missing data. If you have a lot of missing data, then you probably want to consult somebody who's dealt with that problem in a more formal way. But often, I'll be doing an analysis, and one of the important variables in the analysis will be race, and race will be missing on a few % of the people. And although there are fancy things you can do, often you just report that we are missing data on 2% of people, and we've excluded them, or we've included them as a separate category or something. And so do what you can to avoid missing data, but there always seems to be something. So we've got these carefully constructed data files, and now we want to report on them. And obviously, if you do a study, one thing you could do with your data is just give all your data to the reader and say, here's what we've got. But that's not very useful. And the goal is to find trends and important features in the data. And the first thing to be able to, the first thing you need to do is understand the population, understand the sample that you're dealing with. What are these people like in my study? Yes, we've got specific aims about how this treatment affects that outcome, or how this covariate is related to that covariate. And those things will be presented in a research paper as kind of the main findings. But before you can get to that, or before you do get to that, you need to make sure your data are clean. Make sure that you understand anything strange going on, who's in your study, who isn't in your study, what kind of missing data you have, are there outliers, and some of these can be viewed as technical terms or just general ideas. But nearly every research paper starts with table 1 describing the data, and that's for a reason. It's not because people are lazy and say, everyone else did it, I'm going to do it. They're doing it for a reason. We need to know whether the results of this paper apply to everybody or a certain subgroup or something. And so turning our data set into table 1 is an important part of what's going on. When you're reading a paper and you only see table 1, keep in mind that the authors probably generated much more data and many more figures than they have space to produce or put into the paper. And so just the most important information is being pulled out in the most basic way. When you do an analysis, you're going to need to do more to make sure you understand what's going on. And the two important pieces there are the so-called strobe diagram. And it's not for everything, it's about epidemiology. But the idea is this is just an example of one. Is, start with what patients that you had. You excluded them from your study, some from your study for whatever reasons. Maybe some had missing values, so we're excluding them. And you come up with an analysis group. And this is useful to the person reading the paper to say, okay, what's the difference between these two groups? Should I be concerned? Is this group like the group that I want to study, or is it like my patients, or is it different, and therefore the results may not be relevant? So I went to just a random ophthalmology journal and looked at their most recent issue and pulled out their first free article. And this was the table 1 that I found there. And this is a typical table 1 in many respects, but is slightly different in others. First of all, the analysis that they're going to be doing involves comparing better visual acuity measured binocularly, measured better eye, and measured worse eye. And so they're going to compare this to something else that's not even in this table. But because they're pulling these things out of medical records, they actually have almost all this information right from the start. And so they pulled out a sample of nearly 2,200 people. In their analysis, they included 1,800. I say this table is a little bit unusual because often this group, you don't have all the data on. That's one reason they're not included, is because they were excluded for not having some of this data, perhaps. But this group was lucky. They were able to measure all these things. And so we'll have a little bit better sense of, are the people who were included in this study and not included in this study the same, or are they different? So typical table 1 might just have this column. These are the people included in my study. And there are two types of summaries that are given. This group in red for each of the variables, they've given you the mean and the standard deviation, and they tell you the notation right here, mean plus minus SD, and each row has a mean and a standard deviation. The blue box is different. Instead of the mean and standard deviation, it's got the number and the percentage. So each one of these is a count and then a percentage of the total given at the top. So there are several definitions of variable types, and often it doesn't really matter, especially for table 1. Kind of all that really matters is, are we talking about categories or are we talking about numbers? There's sometimes a blur between some of these distinctions. So in certain cases, we'll have to be careful about what type of variable we're talking about, but usually not. But if you have a numeric variable, you usually talk about computing means and standard deviations, and you can do that with ratio variables as well. These don't have enough information to really be talking about averages often. Sometimes these ordinal variables, which just mean the responses are ordered. I disagree with some statement, I'm neutral about some statement, or I agree about some statement. Those I can kind of put in an order, but it wouldn't make sense too much to talk about averaging these values. If one person agrees and another person disagrees, I don't really want to average them and say there's a neutral opinion. Agreeing with something may be much different than disagreeing with it. So in table 1, if you've got categorical variables or for your categorical variables, we're going to report things one way. If we've got numeric variables, we'll report them with means and standard deviations usually. So one of the studies I was working on recently involved diagnosis of an edema, a carcinoma of some kind. Now I'm drawing a blank on what it was, but anyway, so 4 physicians were asked about 40 different cases. So there are a total of 160 observations, and they were asked to make a diagnosis of one type or another, and then they were asked how confident were they. And so there are 160 responses. I can count up how many of each type. Thankfully, there are no missing data, and then compute the percentage out of the total. So this is an example that we didn't see in the table 1 above. Table 1 above either had all the variables were binary, either somebody did something or didn't. So they just reported a single number and a percentage. This is what part of the table might look like if there were, this would be an ordinal variable. This is the least and this is up to the most, and they go in a natural order. And we could report things like the most common observation. We could add these two together in some sense and say at least very confident. So I'm either confident, excuse me, very confident or extremely confident. And so these things are ordered. It makes sense to combine them and talk about at least this or less than that. Here is the distribution not just of their responses, but by the 4 readers, by the 4 graders. And so we can count how many times did reader B give each of these 5 responses, or we could compute some percentages out of those 40. What percentage of the time did they answer each of these responses? And what's nice about this is I can start seeing big differences right away. This person, never gave anything but these two responses. They were never extremely confident, but they were never not confident at all either. They just answered it in one particular way. So that told me something important about these 4 graders that I needed to be careful about with my analysis. It's people grade things very differently on this scale. Some people view extremely confident one way, and they're willing to say it nearly a quarter of the time. And one person was never willing to say that. There aren't a whole lot of options for summarizing categorical data. You've pretty much just seen it all, just numbers and percentages. There are a couple choices that you can make about what percentages. If you just have one variable, it's percentage of the total. If you've got 2 categorical variables cross-classified in this way, and we can talk about within grader A, what percentage of the time did they answer each of these different rows. We could also ask, of all the times that somebody said not confident at all, how often was it person A? That isn't particularly interesting for this analysis, so I've chosen to do these column percentages, but that is one place where you've got some leeway about determining which set of proportions, which set of percentages you're interested in. I mentioned earlier that I mainly use SAS and R for my analysis, summarizing categorical data in R. The main functions that you'll probably use are table function. Maybe you'll add some margins, that sum row at the bottom. Maybe you'll compute some proportions with prop.table. SAS uses proc.freq, and then lots of different options to decide what summary statistics to report. So here's a quick example of analyzing some data in R. This data that I've just loaded, it's got 160 observations. It's the data that we were just looking at. I can compute the counts using the table command. I can compute the percentages using prop.table, and I can join those two things together to make a simple table about the diagnosis. 98 of the 160 were judged to be an adenoma. 62 were not an adenoma. There were 40 observations for each reader. And here's the table we just looked at, the confidence of the decision. This cross-classified table would be something that'd be pretty straightforward to just go through and count up in the records and put the appropriate numbers in each cell. One thing that's nice, and we'll show more of this in a minute, with a statistics package is often you can draw graphs quickly to get a better feel for what's going on. SAS, I'll come back to SAS in a minute. Any questions about summarizing categorical data?
No questions from here, sir.
Sure. All right, you get more choices when you have numerical data because it can have more problems with it in some sense. Categorical data, there's, other than having some missing values, there's not much that can go wrong with it. So because there are things, different things to worry about, there are some different ways to summarize the data. The most common way, and what we saw in table 1 here, was just the mean and the standard deviation. Some alternatives to reporting data in table 1 are the median and the range, the median and the interquartile range, Tukey's 5-number summary, which just is those two things, those last two things combined. Very rarely you'll see the geometric mean and a coefficient of variation. And I'll say a little bit more about each of these, but I wanted to point out that each set of summary statistics has a center, a measure of the center, the mean, the median, the geometric mean, and a measure of dispersion, how spread out are the data, the range, the interquartile range, the standard deviation, and so on. The mean and the standard deviation, I've used fairly straightforward formulas here. What we're going to do is just take each observation, add them up, divide by the number of observations, and you get your mean. The standard deviation is very much the same. We're going to add up and divide by essentially the number of observations. And these are each so-called deviations from the mean. How far is X from the sample mean? Square them, add them up, take the square root. The point is, this is a measure of spread. How far is the point away from the center? The mean and standard deviation are designed and built for, well, they're particularly important for the normal distribution, which is a bell-shaped, symmetric, single hump unimodal distribution. If your data don't follow that pattern, there are other sources, other statistics you can compute. And so if you have highly skewed data, one choice is to report the median, which will be a more typical value than the mean, which might be contaminated by the skewness. The median is just found by ordering the observations from low to high and picking the number in the middle. So if you have 11 observations, the median would be the 6th observation in that list. The range goes from the first observation, the smallest, up to the maximum or the last observation. And that's useful because you can see what the scale of the data are. Sometimes, though, you'll get very outlandish observations. And so you don't really care what the largest value is. You know that's just a fluke measurement of some kind. And so instead of taking the largest observation and the smallest to compute the range, you compute something called the interquartile range, where you find the median of the first half of the data and the median of the second half of the data. And what that amounts to is finding where is the middle 50% of the data. And so it gives you a sense of where the bulk of the observations are. And the 5-number summary is the minimum, the first quartile, the median, third quartile, and the maximum. And that gives you a more complete picture of the distribution, but takes up more space, and journals don't like that. So sometimes you don't get to give them all. There are straightforward commands to compute these summary statistics, both in R and SAS. There's a mean function, there's a standard deviation function, there's a quartile function. In SAS, there's a proc means, where you can list off what statistics you want computed, including the mean, standard deviation, and the quartiles, among other things. In R, let's see. This is a different data set. I'll show briefly. It's got a collection of different variables. One of them is best corrected visual acuity. It's just the denominator. So the best corrected visual acuity is really 20 divided by 1250 in this case. Age in years, lumens, Kelvin, and so on. But we can compute the mean age, the standard deviation of the age, and the range and interquartile range here. So we see that the people we're studying are on average 66 years old, but there's a lot of variability. Standard deviation is 22. And we can see explicitly the range of the data with these quantiles. We had a subject as young as 6 and a subject as old as 99 in this study. And actually, this 6 was an indication that we had done something wrong, because these were all supposed to be adults. And so after reporting this to the investigator, they went and found out that this was actually supposed to be 60. There had been a typo, and we were able to correct that. So one reason to look at your data is to find data errors. All right, so we come back to this table 1 and we see the same, this is the same graph, or same table we saw before, but now we understand a little bit more about what these things are. In this table, they've explicitly told us what they're presenting, so that's very good. Occasionally you'll see tables that don't tell you what's in each row or in each column, and then you're left guessing or having to do some detective work. Be explicit when you can. Write it all out. One thing that happens when you're doing analysis is you become very familiar with the data, and so you know what you're putting in the table, but unless you tell somebody else, they may not know.
Sir, I have one doubt here.
Yes.
Do you always use the logma scale for mentioning the visual acuity, or for the study purpose, it has been converted, or do you measure it in logma directly?
I don't measure it at all as the statistician, but almost always I'm converting Snellen visual acuities to logmars. Occasionally I'm working on a study that where kind of the main importance is visual acuity, and so they take extra time to use the ETDRS chart and the logmar scale directly. But almost always things are recorded as Snellen acuities.
So it's difficult to analyze with the Snellen's chart by itself.
Yes, often. Let's see. Let me show. If we weren't doing age, if we did this best corrected visual acuity, yeah, I didn't want that. I want a box plot. We haven't talked yet about box plots, but I'll just mention it here. Often, if you just look at the denominator, the Snellen acuity, you get this very skewed distribution, and so it's better to convert it to a decimal, and then take the log base 10 to get to the logmar, and then you'll get a much more symmetric distribution. That's a little bit easier to work with. You don't have to worry about the dramatic long tail here of all these people off on the side. everything's a little bit more statistically reasonable.
Okay, thank you, sir.
Yours, yeah. So I've got one here. I'll just point out that this box plot is that Tukey's 5-number summary that I mentioned. It's the minimum, the first quartile, the median, the third quartile, and then the maximum up here. So the 5-number summary and these box plots go hand in hand to describe what's going on. This is a nice graphical representation of the 5-number summary. All right, so graphing is an important part. You often don't get to see box plots about the initial variables, things that go into table 1, but they're important for you to understand what your data are doing. Like I found out that I had somebody out of range on one of my data, but that would have shown up in a graph as well as the table. The great skewness of best corrected visual acuity on its natural scale showed up in a graph. So graphing is a very important part of figuring out what data you have. And I just have a few graphs to show, and then I'll wrap up. I know I'm coming up to the end of my time here for today. Here's a box plot, excuse me, a bar plot for categorical data. This one happens to be the count. You could very easily put it with a percentage instead if you want, but it's a graphical representation of, look, this very confident was the most common answer. We saw that in the table here. It's clear in the graph as well. If you have more than one variable, these bar charts can get a little bit more interesting, a little more complicated. So what were the responses of viewer A for each of these 5 categories, and so on, or you can stack them up. And depending on what you're trying to show, one or the others of these may be more important, but or more useful, I should say. And these are things I just quickly put together. If you were actually going to put these in a publication, you'd spend more time making better legends or better colors or something to make it more useful to your reader. But just investigating it for yourself, you draw things quickly and see if there's anything interesting, and then you can always tidy it up later. I almost always draw box plots, but you can also draw histograms of variables. Box plots usually show you the central tendency with the median. They show the spread. One thing they don't show is if there's several peaks to your data or something. So it is sometimes nice to draw a histogram to see if there are any stray observations or not. SGplot is the main procedure I use in SAS to draw plots, but I actually do almost all my plotting in R. R has had a long history of excellent graphics, either through its base package, which just have a couple functions like hist and boxplot, which will draw a histogram and a boxplot. R has a couple other graphics engines. One's called ggplot2. And of course, it can draw box plots. There's another one called Lattice that's built on the grid system. Anyway, R has many different options for nice graphics. And you can find examples of them online when you need to be motivated to draw a good graph. I've mentioned R, and what I've been showing you is R within RStudio. So RStudio is essentially an editor, but R is the statistical package. RStudio has a nice editor interface and lots of other bells and whistles that make it easier to use R. Both are free for individual use. SAS is not free, but it's kind of industry standard. If you have access to it, it's a good tool to use. Stata has become more popular. It's kind of, I think it was originally used in economics and more of the social sciences, but I see other people using it more often. SPSS is a point and click, or at least does have a point and click interface. It also has a language, a syntax behind it for experienced users. SPSS probably has the easiest learning curve to help people improve, to get going most quickly. Prism is something I've seen quite a bit for people doing lab work. It produces some very nice graphics, but I don't always understand or agree with some of the statistics it chooses to print out. So for me, I'm not a big fan of Prism, but I do know that it's very useful and pretty widely used. Excel and Google Sheets can be used to draw graphs, and I like to think of them though as just more data management. This is where I collect my data and then I read it into one of these other packages. So one of the other points that we're going to address more next time, but I want to remind us of, it was on the list of things to do, is how to interpret our data. And some of the questions you can ask is, well, first of all, are there differences to look at? If you've got a treatment and control group, is there some important difference? Excuse me, are there differences at all? And then, are the differences important, are separate questions. We can look just at some of the summary statistics and say, in our sample, there's a difference between males and females. We might want to then say, is that a real difference? Is that just chance variation, or is it actually something different? And then is it an important difference? And that important difference is rarely a statistics question. It's often a clinical question. If it turns out that men have higher blood pressure than women, or lower blood pressure than women, or I should use a vision example. If the visual acuity of the men in my sample is worse than that of the women, is it a big enough difference that it's important clinically? And as a statistician, I can tell you how big the difference is and give you some error bounds on it, but I'm not a physician, so I can't speak too much to whether it's an important difference. And then why might there be these differences? It might just be chance variation, and that's where statistics come in. It might be bias. How did you select people for your sample? How did you measure the things that you're measuring? And that's where both the statistician and the researcher can have input into why things may be appearing or not appearing. Very rarely do we get to talk about causation in statistics. We're a pretty cautious bunch, and so we often just talk about associations. But there are times when you want to talk about, is this phenomenon causing that result? And there are statistical ways to try to justify claims like that, but they're rare. But when we're interpreting them, we want to say, or we want to be able to consider, is the effect a causal relationship? All right, so just another example of a table one. I'll quickly wrap up here. Sorry for running over. I know it's the end of your day. It's getting late there. Sorry. Clean your data set. It'll lead to a clean analysis. Preparing your data may be 90% of your analysis. It's not interesting work all the time, but having your data in the appropriate format will make life easier. Table one, which we talked about, is the cornerstone of every analysis. Don't just skip over it and say, oh, I'll do it after I do the interesting parts. you got to make the table 1 early so that you can find data errors, you can find unusual things that may affect the analysis that you want to do at the end. So don't skip over it. In fact, in my work for the Women's Health Initiative, when somebody proposes a paper to the planning committee, they essentially have to mock up every single table they might put in their paper, and table 1 is the important one because it lists what variables are necessary for the analysis, and so we can determine whether we actually have the data or not. The interpretation of the analysis that you do in table 1 and the other tables is partly formulaic. We could do some hypothesis test to say, is there a difference or not? But then you need to interpret that, and we'll have a couple of examples of that next time. And it's a little bit of statistical, but mostly it's a logical statement. What else could be going on that's causing this difference? So next week we'll talk about a couple types of statistical inference, how to do some of them in a statistical package, and what they can and can't tell you. That's the inference part, the interpretation part. And we'll talk about how study design can help you draw the conclusions you want to draw. Thank you for your time. I'll stick around if anybody has any follow-up questions. Otherwise, I'll see you again next week.
So just one question regarding the arrangement of numerical data analysis. You had mentioned mean and median. There was one which is also given in books called the mode. Do anybody use that nowadays, or it is just obsolete?
So it's not so much that it's obsolete, but the mode is actually more useful for categorical data. The mode is the most common observation. And if you truly have numerical data, you probably have very few ties. People are spread out along the range of the data. And so it might just be chance that 2 people happen to have the same height or age or something like that. So yes, the mode is reported, but I would report it more in the context of the mode, or the most common response to this question was very confident, as opposed to saying the mode or most common best corrected visual acuity was 20/30 or 6/8 or something.
Thank you very much, Dr. Chris. And we'll meet again next week, next Thursday at 5 p.m. IST.
Thank you very much. It's my pleasure.
Dr. Chris and Dr. Annamalai, just to mention the current scenario here. So we are for analysis, we are using Stata organization-wide.
Okay.
Let you know, and we are also insisting on using using RedCap as a database. At least for the last couple of years, we are using RedCap for all the new studies, and also we are trying to upload the old studies archiving into the RedCap platform.
That's wonderful.
So that is there, and in the headquarters in Madurai, we have a kind of organized biostat support. We don't have anybody senior like you, but we have basic biostatistics support, and so mostly the analysis and data management part, we get support from this team to a great extent. So I'm just giving you the context. So there will rarely be an instance of one of the doctors themselves doing the analysis, actually doing the analysis. But it's very important that they get this understanding so that they can have better discussion with the biostatisticians, and also understand, why they're asking for certain things.
That's great. That's very great that there's support, statistical support, and I agree that the interaction between the statistician and the physician is very important. and I work hard to understand what the doctors are bringing to the table, and hopefully this is helping some of the residents figure out what the statistician is thinking about.
Yeah. So this was like a very nice introduction for those who have not got very good orientation to statistics. So that way, so we're looking forward to the next session.
Great. Thank you very much.
Thank you very much, Dr. Chris.